let's wait for a couple of minutes and then I will start. Okay, so let me start today. I hope the screen is visible. So today is the week 5 of the problem solving session of the course that Introduction to Atmospheric and Space Science. So first I will discuss the assignment, and after that regarding the assignment 6 I will try to give some insights of the theoretical aspects, because mostly it is theoretical, it's not too much of numerical, so I will give that. But before that let me discuss the assignment questions. Okay, so this is the week 5 assignment, where the first question is based on the first law of thermodynamics, which says the first law of thermodynamics is based on conservation of what? So the options are energy, heat, entropy, and mass. So we all know, in fact from 11 and 12 whatever we are studying in thermodynamics, we know that the first law of thermodynamics is related to the conservation of energy. So the correct option will be energy. Second question is, the internal energy U of an ideal gas is a function of, see, it's a function of temperature, no doubt, because as the temperature decreases, we have discussed in the previous session that when a parcel, let me show here, not this one, yeah. So when a parcel, suppose this is a parcel, when it goes up, so what it tries to do is that it tries to keep the pressure same as that of the environmental pressure. So P is always equal to P. So in order to do that, its volume should increase. So to increase this volume, some work needs to be done. So because of this work is done by the expense of the internal energy, as a result of which the temperature also decreases. Therefore, internal energy, of course, is a function of temperature, and internal energy is also a function of the state. So suppose this is the first point and this is the second point. So this is the first state and this is the second state. So from here to here, if we join, then the internal energy, the change in internal energy will be u2 minus u1. It does not depend on the path. It does not depend on the path. It only depends on the final and the initial points. Just a minute. I hope the screen is visible. Some internet connection. I am switching off the video. Okay. So what I was telling is that if 1 and 2 are the initial and the final points, then the change in the internal energy will depend on the second state and the first state, the final and the initial. It does not depend on the path. So it's a function of state. Therefore, if we come to the question, here, so internal energy of an ideal gas is a function of both temperature and state. That should be the correct option. Okay. The third question is the difference between the specific heats at constant pressure and constant volume of dry air is. So as we can see, we have already discussed that for dry air, CPD minus CVD is equal to RD. So CPD minus CVD is equal to RD. So if you see, instead of dry air, if you see the vapors, for vapors also this is true. CPV minus CVV is equal to RV. So for specific gas constant as well as for the universal gas constant, these things are always same for 1 mole of gas or 1 kg of gas. So for dry air, CPD minus CVD should be equal to RD. Okay. So the difference between the specific heats at constant pressure and at constant volume of dry air is 287. Fine. Now for an ideal monoatomic gas, the ratio of the specific heats at constant volume and constant pressure is CV by to CV is what? So for monoatomic gas, we have discussed in the earlier class also. So for monoatomic gas, let me write. For monoatomic gas, we have degrees of freedom is 3. Fine. So if this is the degrees of freedom, then CV will be equal to 3 by 2 kb and CP will be equal to 5 by 2 kb. Therefore CV by CP will be equal to 3 by 5. And in the question it is CV by CP, so it is 3:5. The next question is the ratio of specific heat at constant pressure and specific heat at constant volume is always. So we already know this relation that CP minus CV is equal R. So the CP minus CV is equal to R, so CP should be equal to CV plus R. Therefore CP is always greater than CV because R is always greater than 0. Therefore if CP is greater than CV, therefore CP by CV is always greater than 1. CP by CV is always greater than 1. Okay. Now, the next question is, in an adiabatic process, the dash remains constant. Well, here the first option is PV to the power gamma. The second is pressure, third is temperature, and fourth is volume. And the correct option as per given is temperature, which is not correct. Temperature is constant only in the isothermal process. We all know that. Volume for isochoric process. Pressure for isobaric process. So PV to the power gamma is the only option which is correct for the adiabatic process. So the right answer should be PV to the power gamma. It's not temperature. Okay. The next question which is present here is that the calculate the value of the dry adiabatic lapse rate. So the value of the dry adiabatic lapse rate, if these conditions are given, so the value of the lapse rate, if these conditions are given like 9.8 and 1 kilojoules per kg per Kelvin, this I will solve. The eighth question is also a numerical question, so I am having this. Ninth is also same. And an air parcel in the atmosphere continues to rise until it becomes saturated. Okay, so this is the correct option, of course. And which of the following is or are correct at dew point temperature? So in dew point means that relative humidity is 100%. So air is completely saturated with respect to plane surface of pure water. Therefore, so all these three things are correct. I will today discuss also about some more insight. I will give more insight about dew point. So that will be more clear. Okay. And the last question is, the latent heat of condensation is equal to the latent heat of vaporization. So it's just the process, opposite process. Condensation, that is from vapor to liquid phase, and vaporization from liquid to vapor. So vaporization is from liquid to vapor. So therefore, latent heat of condensation is equal to latent of vaporization. Now other three numericals I will solve. Okay, so this is the question from the assignment only, which is a numerical based question. So I will derive first that what is the dry adiabatic lapse rate, and then calculate the value. Okay, so question is that calculate the dry adiabatic lapse rate if G is this and Cp is this. Well, first of all, Cp is given to be 1 kilojoules per kg per Kelvin. So in joules, we can write it 1000 joules per kg per Kelvin, right? G value is given 9.8 meter per second square. These are given things. Now, according to first law of thermodynamics, which we mostly use in meteorology, that is delta Q, or let us write it in specific terms, in smaller terms, that will be equal to Cp dt minus alpha dp, where this is the change in enthalpy and this is the alpha is the specific volume, and this is the change in pressure. Well, now this is for adiabatic lapse rate and dry. Therefore, for adiabatic process, we already know this thing. Delta Q is 0. Fine. For adiabatic process, delta Q is 0. Therefore, 0 is equal to Cp dt minus alpha dp. Now question is, this is a dry air. So dry air means Cp will be what? Cpd, the dry, and that value is only given. So it's fine. Now alpha can be written as what? It's actually 1 by rho. Therefore it will be R d T by P. Why RD? Because it's a dry. Fine. Therefore 0, or let's see, or 0 is equal CPD dt minus RD T by P dP, right? Just keep this term on the left hand side, so I get or minus CPD dt by T will be equal to minus RD dP by P, because T I have already taken. Cancel out the negative sign, therefore I get just you have to integrate now, so dt by T will be RD by Cp dP by P, right? Therefore log T, or we don't need this. Well, this is actually what I am doing for the potential temperature thing, but for adiabatic lapse rate, but let me complete it. From T to theta, this is P naught to P. Okay. Oh, sorry, this is P naught, this is P. This is 1000 millibar. Okay. Therefore, theta, I have already given the expression in the previous class. So it will be like this: P naught by P to the power RT by Cp. D. So this is the potential temperature equation, but we are more interested about the dry adiabatic lapse rate. We are more interested about that. So I have gone in a different direction. So this, from this only we can calculate. See, Cp dt or Cpd dt will be equal to alpha dP. Just differentiate with respect to z. Therefore Cpd dt by dz. Why am I doing differentiating with? Because this is lapse rate, and lapse rate means rate of temperature with height. That's why I am differentiating. Okay. Now this will be alpha dP dz. Fine. Now dt dz I keep it here as it is. This will be alpha by Cpd. dP dz can be written as minus rho g from hydrostatic equation. Now this alpha is nothing but 1 by rho. Therefore this alpha and rho can be chopped out. So it will be minus g by Cpd. And all the values are given. So 9.8 divided by 1000. Right? So that comes out to be about 0.098 0.0098 Kelvin per meter, or 9.8 degree Kelvin per kilometer. This is the gamma D. Okay, and gamma D is now nothing but minus dt by dz, because I have taken this minus sign in this side. Okay, so this is the value of the dry adiabatic lapse rate. This is the extra thing which I have done. Don't need to follow this because I have already derived it, the potential temperature. So this is the potential temperature. Okay, fine. So from this equation we have come here. Okay, fine. The second question from the assignment only is that an air parcel rises from the surface at 1000 MB. So this is the 1000 MB and this is 700 MB. So let us consider this is 1000 MB surface, pressure surface, and this is 700 MB. Without mixing with its surroundings, if its surface temperature is 25 degrees Celsius, what is the final temperature? I mean, over here, what is the temperature? Okay, so for that, what I do is that use hydrostatic equation. It's a simple method through which you can go near to the answer. Hydrostatic equation. What is that? dP is equal to minus rho g dz. You see, of course, this rho will change. It will change as we go higher. But in the column, let us assume which is the actual value of air, so rho air, which is equal to 1.028 kg per meter cube. We can assume this. G we know is 9.81 meter per second square. Okay, so now what we will calculate is dz corresponding to dp. So dp is what? dp is final, that is 700 mb minus 1000 mb. See, remember this is in millibars now. You have to convert into hectopascals to pascals. So now it is in SI unit pascals. That will be equal to minus 1.028 into 9.81 into dz. Fine. So it will be minus 300 is equal to minus 1.028 into 9.81 into dz. So minus minus I can chop out. Now if you calculate it, let's calculate it. 300 9.81 and divided by 1.028. So it's about 2974. So dz is about 2974 meters or 2.9 kilometers. Okay. Okay. Now temperature, final temperature, that is at 700, will be therefore or temperature at 2.9 kilometers from the surface will be equal to T naught minus gamma z, and take it dry. Consider it as a dry air, therefore gamma will be equal to gamma d, which we just found out, that is 9.8 Kelvin per kilometer, right? Kelvin or degree Celsius, whatever you want, because it's a change. So T naught is how much? 25 degrees Celsius. Keep it in Celsius, it does not matter. Minus gamma. Gamma is 9.8. Since it is in kilometer, I will write it 2.9. So how much it is? Let's see. 2.9 into 9.8 is 28.42. So it will be 25 minus 28.42 minus 25. So it comes out to be minus 3.4 Kelvin or nearly equal to minus 4 Kelvin. So this density 1.028, if you assume it to be 1 kg per meter cube, it will come out to be nearly minus 4.3 Kelvin. So therefore the correct option, which goes very near to 4 degrees Kelvin, so about 4 degrees Celsius, not Kelvin, it's Celsius because all are in Celsius scale, right? So this comes out to be about 269 Kelvin. Fine. Okay. Now the next question is based on the mixing ratio. We have done several questions related to this in the previous class. So in this we have, if air contains water vapor with a mixing ratio of 5.5 grams per kg and the total pressure is this, the vapor pressure is simple. So mixing ratio we can define, say W, or you can say with R, whatever, that is equal to epsilon E by P, where epsilon is 0.622, E is the actual vapor pressure which is need to be found here, actual vapor pressure, and P is the total pressure. This is given that W is equal to 5.5 grams per kg, and we can say that it will be 0.0055 is the W, because kg per kg is 1. So 0.0055 is equal 0.622 E divided by 1026.8. Okay. Okay. Now some calculations has to be done. Okay. So it will be 0.0055 into 1026.8 divided by 0.622 is equal E, which is the actual vapor pressure which we need to find out. Okay, so if you calculate it, let's calculate it. It comes out to be 0.0055 into 8 divided by 0.622. Well, it comes out to be about 9.07. So it is 9.07 in millibar. Why? Because this I have taken in millibar, remember. So this is this, or correct option may be 9.1. Okay, this is the thing. Okay, this kind of question we have already done. So the entire assignment is, I think, now finished. So we will go to the some more thermodynamic theories today, so that it is helpful for all of you to understand the questions in assignment 6, solve them properly. Okay, so fine. Okay, now this is about the saturation vapor pressure. So what is this saturation vapor pressure? I will tell you. So suppose you have a container which is here and it's filled with water. So what is happening is that as the temperature is suppose T here, so water molecules tends to convert into vapor by gaining the latent heat. So it takes up the latent heat. So remember always that evaporation takes up latent heat, okay, and then only it will convert from liquid to vapor, water to vapor. That is the evaporation. Fine. Now if we cover this container, now there is a covering, then what will happen? See, if temperature is maintained here, still the vapor molecules will form, but after some time what happens is that the vapor molecules will be enough such that the rate of evaporation at that time, will be equal to rate of condensation, because the vapor molecules cannot escape here. So vapor molecules will remain here. So one after another, when the water molecules are converted into vapor molecules here, there will be enough vapor molecules, and as a result of which now they cannot escape anywhere. So this is the time when the rate of evaporation, that is one water molecule, if it converts into a vapor molecule, then one vapor molecule should also convert into one water molecule. This time these two processes, and one water molecule will convert into one vapor molecule. Okay, so this is the time when rate of evaporation is equal to rate of condensation. And what is that? When any rate of the opposite processes are equal, we call it to be an equilibrium. So when there is a maximum amount of vapor pressure, that is enough vapor pressure, after that if extra vapor molecule comes, then it will condense again. One of the vapor molecule will condense. At that point, whatever the pressure exerted by the vapor, that is known as the saturation vapor pressure. Saturation vapor pressure. So it is what? Maximum vapor pressure or maximum vapors when rate of evaporation will be equal to rate of condensation. At that time, whatever the maximum amount of vapor which is present and its corresponding pressure, so maximum pressure I can say, so maximum pressure of the vapors when the rate of condensation is equal to rate of evaporation. So that is the saturation vapor pressure, and this saturation vapor pressure is also called as the equilibrium vapor pressure. Why? Because rate of evaporation is equal to rate of condensation. So this is the simple concept of the saturation vapor pressure or equilibrium vapor pressure. So when you cover up in a container and maintain a temperature, vapor molecules will start forming over these regions. But a time will come when vapor molecules, as vapor molecules cannot escape, so vapor molecules will continue to form. But a time will come when one further extra vapor molecule it comes, then one of the vapor molecules will condense into liquid or water. That point, whatever the vapors are present in above this water level and the amount of pressure which is exerted by those vapors, that is known as the saturation vapor pressure. That is the concept. Okay. And generally it is represented as ES. See, E was the actual vapor pressure when it is not saturated, and ES is the saturation vapor pressure. Right? Okay. Now comes a very important equation, although I don't know whether it will be used in this course or not, but it is very important to understand the saturation vapor pressure properly. So this is the Clausius-Clapeyron equation. It deals with the phase. So we have, suppose, pressure and volume, P alpha diagram, specific volume I am drawing. Here I am drawing specific volume. Specific volume is drawn here. So, so this is the phase diagram generally looks. Okay, so this is the process. So this is say 1 and this is say 2. Actually this region is vapors, this region is liquid. So you can see that vapors are compressible whereas liquid is incompressible. Why? Because if you see here, if you give more pressure, very little will be the compression. So you take these two regions, see the change in pressure is huge, but the change in delta alpha is not so much. But here in this case the change in pressure is not very high, but you can see that alpha, delta alpha will be very high. So vapors are more compressible as compared to the liquid, and also alpha of vapors will always be greater than alpha of liquids. You can see that from this phase diagram. Okay. So it deals with the phase diagram. What happens is that this is the region where if we give slight increase in pressure in this one point, just to the right of that it is completely vapors. Now to the left, if we give some small amount of pressure increment, then entire vapors will be converted into liquid. So this pressure in 2 or in 1, whatever you say, this is the saturation vapor pressure. Why? Because all the vapors are converting into liquid at this pressure, and this is the pressure which we have discussed is the saturation vapor pressure, right? ES. So in 1 to 2, if we apply first law of thermodynamics, so if 1 to 2, if we apply first law of thermodynamics, we can write in the terms of entropy. So T d5 will be equal to du plus Es d alpha. Why? Because we are concerning about this 1 to 2 process, and here it is also Es, here it is also Es, So ES1 minus ES2 is nothing but the DES. If we I will show. Okay, so this pressure is also the same saturation vapor pressure, but there is some small increase. Okay, this pressure is entirely saturation vapor pressure. Okay, now this is for a particular temperature T1. Fine. So this will be the equation, and this is from 1 to 2. If you integrate, this will what it comes. Okay, now what I will do is that I can write this as T phi 2 minus phi 1. This phi is the entropy. I am actually writing the dq is equal to T d phi, and you can call it as a specific entropy per unit mass. So that will be equal to U2 minus U1 plus ES alpha 2 minus alpha 1. Right? Now I take all the two terms on the left hand side and on the one terms to the right hand side. Right? And let that be equal to x. So what will be dx? It will be T d phi 2 plus phi 2 dt minus du2 minus es d alpha 2 minus alpha 2 des will be equal to T d phi 1 minus du1, oh sorry, this will be plus phi 1 dt minus du1 minus est alpha 1 minus alpha 1 des, that is equal to dx. Now we already know that T d phi minus du minus es d alpha will be equal to 0, right? Because according to the first law, we know this. Okay, so if you put it here, then what will happen? We have this T phi d d phi 2, this and this chopped out, this and this chopped out. So what is remaining here is phi 2 dt minus alpha 2 des will be equal to phi 1 dt minus alpha 1 des. So now it will be phi 2 minus phi 1 dt will be equal to alpha 2 minus alpha 1 des. So we can write des by dt will be equal to phi 2 minus phi 1 divided by alpha 2 minus alpha 1, or this can be written as, since this is the phase change from vapor to the liquid in between 1 to 2, so we can write it as L 1 to 2. This is the latent heat divided by temperature alpha 2 minus alpha 1, right? So this is the formula when you change the temperature. So suppose this is another plot for T2. So whenever you change from T1 to T2, the ES changes, and that change in ES, the DES, is actually this quantity. Okay. Now you see, from 1 to 2, that is from vapor to liquid, when it is converted, latent heat is released, right? So if it is released, then what will happen? There will be a negative sign. So I will say that from 1 to 2, latent heat is released, right? Because it is from vapor to liquid. Therefore L12 should be negative or less than 0, right? Now if it is less than 0, again you see that negative which you have, I am absorbing it, des dt, that will be equal to L12 divided by T alpha 1 minus alpha 2 by, this is now the modulus. So you put the actual value of the latent heat of vaporization. This value is this L12 is actually 2.5 into 10 to the power 6 joules per kg, right? So this is the latent heat divided by T, and alpha 1 minus alpha 2. Well, alpha 1 is this, because this is corresponding to 1, so this is alpha 1, this is corresponding to, this is alpha 2. So alpha 1 is always greater than alpha 2 because of this. Therefore, you can see it that it is matching. So this is the Clausius-Clapeyron equation, which further gives you, okay. So from Clausius-Clapeyron equation, let me write, from Clausius-Clapeyron equation, we have that expression which we have, ds dt will be equal to L12 divided by, or you can write LV, latent heat of vaporization, temperature and the change in the specific volumes. Fine. This thing can be written as ES, which is a function of temperature, is A e to the power minus B by T. So you can see the saturation vapor pressure is just a function of temperature, where A is some constant which is 2.53 into 10 to the power 11, and this B is minus 5420, plus. Okay, so it's a function of temperature. Now see, this is the graph. Sorry. So this is the saturation vapor pressure with temperature, but actually this is not saturation vapor pressure, this is actually the actual vapor pressure. Actual vapor pressure. And this thing, this line is actually E is equal to ES. When E is equal to ES, that is actual vapor pressure becomes equal to the saturation vapor pressure, then that is this represented by this line. Okay, this entire line which I have drawn. Okay, fine. But now I want to discuss about this dew point and wet bulb processes, and then I will show in this figure how to understand using this particular figure, that is saturation vapor pressure with temperature, where we will get the dew point, where we will get the wet bulb. So, but before that, the processes should be known. Okay. So first is dew point. Just a minute. Okay. So this is the dew point. See, there are two processes. First of all, this dew point and wet bulb process, all are the processes. These all processes actually converts unsaturated air parcel to saturated air parcel. Now question is, how we can convert, or what are the ways through which we can convert these unsaturated air parcels to saturated air parcels? This is we need to know. So first is, if we cool an air parcel in same pressure level, that means what? At same pressure level. Say I have an air parcel at 850 hectopascals. Now in that same 850 hectopascals, I decrease the temperature in some way. So that means what? This is isobaric. So isobarically, if we cool an air parcel, then we can saturate an unsaturated air parcel. This is one way we can perform this. Another thing is that you cool, but at the same time cool the parcel and at the same time you add moisture. Okay, so if you add some moisture in a unsaturated air parcel, if you adding moisture, Q suppose specific humidity or more moisture you are adding, then of course it will saturate out. And if you cool it down, so again there is a chance that it will be saturate out. So these are the two processes through which we can uh, convert an unsaturated air parcel to a saturated air parcel. Oh, of course we know, because as the temperature decreases, uh, we see that condensation droplets on cloud condensation nuclear or some different particles over which we can see that droplets are forming. For example, you take a bottle of water from the refrigerator, then you can see that some small droplets forms. Why? Because the temperature is low and outside the temperature is high as well as moisture is present. So cooling can lead to saturation, as well as moisture adding can also lead to saturation. The first process which I have shown or told here is actually the dew point process. So what is dew point? Let me write. The temperature at which unsaturated air parcel gets saturated when it is isobarically cooled without adding moisture. And what is wet bulb? This is also a temperature. So the temperature at which unsaturated air parcel gets saturated when you cool isobarically but also adding moisture. So that temperature is the wet bulb temperature. Okay. Now I will show you here where will be the dew point. So suppose any parcel is at having temperature 35 degrees Celsius. Okay. Any parcel has a temperature 35 degrees. So this is 35. So the saturation vapor pressure is here, right? But the actual vapor pressure is this amount. This is the actual vapor pressure. This is E and this is the ES. Okay. So these are the two values. So it is not saturated. Of course, when E will be equal to ES in that parcel, then only it will be saturated. Actual vapor pressure equal to saturation vapor pressure. That is the saturation. So E is less than ES for this parcel at 35 degree Celsius. Great. Now I isobarically cool it. So you cool it. You are not adding moisture. So you are just cooling it. That means E is constant. Not adding moisture. Not adding moisture. That means what? Vapor pressure will remain same. E is constant. Right? So you are cooling it because temperature is decreasing here in this direction. So when it becomes saturated, here it becomes saturated. That is E becomes equal to ES. That temperature, so it comes out to be mostly near this, some 26 degrees Celsius maybe. So this becomes your T dew point temperature. Because why? Because you are isobarically cooling only. That's all. Now for wet bulb, what is happening? You are cooling isobarically, but as with that, you are also adding moisture. So if you are adding moisture, so if moisture is added, if moisture is added, then what will happen? So let me change the color. Wait. Yeah. If moisture is added, E is not equal to constant, but E increases. So I increase, but at the same time I'm cooling. Suppose this way I am increasing the moisture as well as cooling. So this temperature, okay, this temperature, say 29 degrees Celsius, is your T wet bulb. Okay. Therefore, what we have seen is that T dew point, or I change again the color. Wait, first erase it. Change the color with this. Okay, so what relation we have got? The temperature which we have, we call it a dry bulb temperature because it's a dry air's temperature. T dry, which is nothing but T, which is shown here, okay, that is greater than T wet, of course, because it is cooled, and as well as the moisture is added, and you have T dew. So this is the final relation. Dew point is the minimum. After that, it is the wet bulb. After that, it is the dry bulb. So this is the relation which will hold everywhere. Fine. So this is a graph which is extremely important to understand. Okay. Change the color to this. Fine. Fine. The next slide is about the relative humidity and saturation mixing ratio. Just a minute, let me see. Okay. So these are the simple definition. See, relative humidity is, let me define it. Oh, sorry. Okay. So relative humidity is actually defined as the actual vapor pressure to that of saturation vapor pressure. And generally, if you have ever looked at any the weather updates, then you can see that relative humidity is 35%, sometimes 77%, sometimes 95%. So in percentage it is done. So therefore RH, the relative humidity, is actually E by ES, actual by saturation vapor pressure, into 100%. Okay, this is the relative humidity. Another way it is defined, that is RH is equal to W by WS into 100%. What is that? W is the actual mixing ratio and divided by saturation mixing ratio. Simple. See, the saturation vapor pressure, we have understood the concept of the saturation vapor pressure. See, the mixing ratio will be WS, the saturation mixing ratio, on the other hand. So saturation mixing ratio is just written as same as the formula of the mixing ratio, epsilon ES by P. Instead of E, we have ES, saturation vapor pressure. So this is the WS. So if you do this, it will be nothing but epsilon E by P and epsilon ES by P. Epsilon P comes chopped out, it is 100%. Same. So relative humidity is equal to this. So this is the saturation mixing ratio and uh, the relative humidity. Fine. So this is a small question based on the saturation mixing ratio. It's very easy. So let's solve it. If a temperature of a parcel at 700 hectopascal surface is 10 degrees Celsius, so you have parcel whose temperature is 10 degrees Celsius. Again, you have to convert it always to Kelvin. So it will be 283 Kelvin, and the pressure is given to be 700 hectopascals. At that level the parcel is there. So what is the saturation mixing ratio? So I have already written the formula of the saturation mixing ratio. What is that? Ws is equal epsilon Es by P. And see, epsilon is known, P is known. What is Es? See, Es I have already shown that it is a function of temperature, right? So Es is a function of temperature. So Es is, I have already written it, e to the power minus b by t. So if you do it, Es will be equal to 2.53 into 10 to the power 11 into e to the power minus 5420 divided by 283. Let's do it. So it will come out to be about 1217 and some more digits are there, point something. So it will be in pascals. So this will be 12.17 hectopascals. So this is the saturation vapor pressure. Let me again check the calculation. Yes, 1217.69. So it's fine, 12.17 hectopascals. Remember, this formula is in pascals. Okay, so ES we have found out. Now we need to calculate WS. It's very easy, 0.622 into ES 12.17. I'm not converting from hectopascals to pascals because pressure is already in hectopascals. 700. That comes out to be about, let me calculate. So it will be 0.622 into 12.17 divided by 700. It's about 0.0108. So what is this? It's about 10.8 grams per kg, which is very high. Fine. Okay, this is a small numerical based on that. Okay. The next thing is the dry adiabatic lapse rate, which I have already shown, but I will, through the figures, I will try to illustrate that what is actually happening when a parcel is dry adiabatically moving upward or downward, and then the moist adiabatic lapse rate, that also I will discuss shortly, and after that the concept of stability and instability I will come. Okay, just a minute. So dry adiabatic lapse rate I have already calculated in the beginning. Okay. And that comes out to be gamma D, or you write it as gamma D, whatever you be. So that will be G by Cp, and that comes out to be about 9.8 degree Celsius per kilometer, right? This I have already seen, or you can change it to 10 degrees Celsius per kilometer as per your wish. Now suppose this is a surface, and at surface a parcel is there whose temperature is 20 degrees Celsius. So what will happen at 1 kilometer? What will happen at 2 kilometer? So 1 kilometer, this is 2 kilometer. Fine. So we know as this parcel goes up, the same thing we have to remember. As the parcel goes up, parcel's theory is based on the fact that parcel at any level, its pressure inside the parcel should be equal to the pressure at the environment. That should always follow. So at 1 kilometer it will follow at 2 kilometers as well. So if the pressures are same, then the volume should have to increase, because according to the ideal gas law for a particular temperature, so the volume is increasing. Now how the volume is increasing? Some work is done to increase the volume. So if some work is done, which is driving this work? That is the internal energy. So internal energy is lost to do work so that the volume increases. Okay, so this loss of internal energy is resulting to the decrease in the temperature, and we see that the decrease is about 10 degrees Celsius for kilometer. So this comes here, and so parcel becomes bigger, it becomes 10 degrees Celsius. Again it goes up, it becomes further bigger, and it comes out to be about 0 degrees Celsius. Okay, so in this way it follows. Another important aspect is there, which is environmental lapse rate. You need to understand this environmental lapse rate. See, it depends at different location. Location wise it changes. Location wise changes. But the mean, if you do the global mean of this environmental lapse rate, it comes out to be nearly about 6.5 degrees Celsius per kilometer. Fine. So this is the parcels, but what about the temperature of the environment? See, at the surface temperature is 20 degrees Celsius of the environment. Let me write it with a different color, that will be helpful to understand. So for environment it is 20 degrees Celsius. At 1 kilometer height it will be how much? About 13.5 degrees Celsius. At 2 kilometer what it will be? About 7 degrees Celsius, right? So what is happening? See, this is cooler than this. So if any object is cooler than the environment, then what will happen? It becomes more dense than this, and hence what will happen? It will fall down. So it will not go to 2 kilometer, it will not go even to 1 kilometer, because at 1 kilometer only the environment's temperature is 13.5 degrees Celsius, which is greater than the 10 degrees Celsius. So it will not go, it will fall until and unless some other thing is there which is lifting this parcel up, it will fall down. Okay, so from here is the concept of stability and instability comes. Fine. So here we have discussed that it is a dry adiabatic lapse rate whose value is about 10 degrees Celsius per kilometer, and if the parcel's temperature at the surface is 20 degrees Celsius, environment is also same. Now as we go to 1 kilometer, environment's temperature decreases by this, and dry adiabatic lapse rate is this. So if it's a dry adiabatically, if the parcel moves, then at 1 kilometer it is 10 degrees Celsius, but at 1 kilometer the environment is 13.5 degrees Celsius. So it is less dense, environment is less dense as compared to the parcel. So parcel being heavily dense, it should fall until and unless something is there to balance. So this is the concept here. Fine. Now change the color again. Now this is the moist adiabatic lapse rate. So this is the moist adiabatic lapse rate. So moist adiabatic lapse rate is generally taken to be 6 degrees Celsius per kilometer, and you have seen the complete derivation in the, I think, week 5 it was there, about the saturation adiabatic lapse rate, which depends on so saturated adiabatic lapse rate, it depends on, is a function of temperature and pressure. Why? because it depends on the mixing ratio, and mixing ratio depends on this. Fine. So moist adiabatic lab state comes out to be 6 degrees Celsius per kilometer. We generally take it. Now what happens if we do the same picture here? So this is surface, this is 1 kilometer, this is 2 kilometer. Okay. So this is surface 1 and this is 2. So this is again a parcel. So it is now moist adiabatically rising. So it is again 20 degrees Celsius. What happens here? It increases. Of course it increases. Of course it increases in 1 kilometer, and it becomes further bigger, and it comes out to be about I think 8 degrees Celsius. Now what happens in the environment? Let me change the color again. At environment it is 20 degrees Celsius again, but here it is 13.5 degrees Celsius, but here it is 7 degrees Celsius. So consider at 1 kilometer, what is happening? This parcel's temperature is higher than this. So what will happen? Its density will be lower than this, so it will go up. Again in 2 kilometers it is 1 degrees greater, so again it will go up. So what is happening in the moist adiabatic lab state? What is happening in the moist adiabatic lab state is that since it is moist, some kind of latent heat is released as vapors, or I would say saturated vapors, are converting into water droplets. And this latent heat is actually helping the parcel to become buoyant, and hence the temperature is rising and it goes going up. So if you compare the dry adiabatic lab state with the moist adiabatic lab state, then you can see that this is the condition which is happening. For moist adiabatic lab state, as the name suggests, it is moist or saturation adiabat. So in this process, latent heat is released when saturated vapors are converting into condensation droplets. Latent heat is actually helping the parcel to go up, which is not the case in the dry adiabatic case. No moisture, so it is just the temperature is dryly decreasing, and hence it is very difficult to put the parcel up until and unless some perturbation, or not perturbation, some disturbances are there. So we will discuss those disturbances just after this. So now this is the stability and instability, which is an important process when now after stability and instability, it's a cape and sign, and then the convection process I will give it in very short, and then clouds. Fine. Okay. For stability and instability, a very important thing which we need to know is the buoyancy. We have all studied this, but in case of atmosphere, so two things are there. One is the parcel, and another is the environment. So this is parcel and this is the environment. Okay. So the temperature is T parcel and density is rho parcel. This is temperature of the environment. This is rho of environment. Okay. This is rho of environment. So what happens is that suppose you have a parcel. Okay. Now outside the density is rho e, this is rho p. Now there is a gravity which is acting and there is a buoyant force which is acting. Now when this means, by clear common sense, when this parcel will go up, This parcel will go up when its density rho p is less than rho e. Of course, because it is less dense, that's why it is going up. If it is highly dense, it will fall down. So take it a reference. Let this be z or delta z. Then this delta z double dot will be equal to what? Or the mass, if you write for the parcels acceleration, so it will be rho p into g into delta z double dot. Oh, sorry, rho p into v, volume. Sorry. So rho p into volume into delta z double dot will be equal to when? Means the delta z double dot will be positive when? When this rho e minus rho p is a positive quantity into v into g, right? And I can chop out the v, so delta z double dot will be equal to rho e minus rho p divided by rho p into g. So this is the acceleration. So you can see now, if you put rho e which is greater than rho p, that is environment is highly dense than this, the acceleration is positive, that is in the positive k cap direction. But if it is opposite, it is negative. Fine. Now you can write it in terms of temperature also. How will you write? Now delta z double dot will be equal to P by RTE, P by RTP divided by just a minute. Just a minute. Okay. So P by RTE minus P by RTP divided by P by RTP into G. Now you can question that why the P is not changing, because again the parcel theory suggests that at any level the pressure in the parcel will be equal to the pressure at the environment. So therefore the P's are same, the pressures are same, and R is a constant, so it's not to worry about that. Therefore delta z double dot will be how much? It will be, so if you rearrange this, it will come out to be T parcel minus T environment divided by T parcel divided by, or I think T environment, sorry, T environment divided by G. Now in terms of lapse rate we can write. How can we write? So delta z double dot will be equal to delta Tp by delta z minus delta Te by delta z into G by Te. So what is this? Parcel's temperature by this will be gamma of the parcel minus gamma of environment into G by Te. Now this in times delta z has to be delta z, right? Because I am differentiating with delta z, so must be multiplied by delta z. So this is delta z double dot. And actually this thing is nothing but n square, but n square is the Brand-Weissler frequency. Or buoyancy frequency. So we call a parcel is stable. Just a minute again, some network issue is there. Okay, so this is the n square, the Brand-Weissler frequency or the buoyancy frequency, whatever. So now So this is the frequency which is there. Okay, now therefore n square is equal to gamma p minus gamma e divided by Te into G. Now we call the parcel to be stable when gamma p is greater than gamma e. If gamma p is greater than gamma e, then n square is greater than 0. Parcel, oh, I'm sorry, this is gamma p is less than, or something, I have done something wrong. Yeah, so this will be minus, I'm sorry, this will be minus and this will be plus. Actually this is plus and this is minus, but when we do this thing, this should be like this. Okay, therefore it will be minus gamma p plus gamma e. Now therefore if gamma p is greater than gamma e, then n square will be less than 0 and we have partial oscillation, that is stability. But unstable condition is that when gamma p is less than gamma e, where n square is greater than 0. Fine. In that case, parcel goes up. And this is quite related to that, what we see, that this is the condition and this is the condition. If a ball is here, if you force it in this direction, it will come back after some time. So this is what you call as a stable situation, like this, where parcel, if it goes up, it will come down. Whereas in case of unstable, if you throw this ball or just push it, it will never come back, it will go up. So this will continuously go up. This is the unstable situation. So this is the concept of stability and instability. Remember, this lapse rate which is there is actually negative, right? The rate of decrement. That's why this minus I have not taken, which is wrong. So this minus needs to be taken. Fine. This is done. Next is cape and sin. Actually what happens is that this is T d log p graph, but if you say that this is a height and this is suppose the temperature, so what is happening is that, or some height, or you can pressure level also. So this is suppose your dry adiabatic lapse rate with this gamma d, and this is the environment, and this is the saturation lapse rate. So what is happening? Initially the parcel is starting from here, and as you know that gamma d is about 10 degrees Celsius per kilometer. You know gamma e is roughly about 6.5 degrees Celsius per kilometer decrement, and this is shown with a green line, and this gamma d is shown with a red line. So what is happening is that this temperature, parcel's temperature is decreasing than the environment. But why is it rising? If the parcel temperature is greater than less than the environment, then it will fall, right? So if it what is happening is that this is gamma d is negative. Remember, this is 10 degrees Celsius decrement, 6.5 degrees Celsius decrement, which is shown here, quite well. Now just a minute, some problem in the internet. Okay, some connection issue. So this is the situation. If the temperature of the parcel is lower than the temperature of the environment, it should fall down because it is stable. But I am saying that by some process it is going up, suppose, and I will show what are those processes. And these are the processes like thermals, low pressure, fronts, and this orographic lifting. These are the processes called the convection, through which it is forced through a particular level to a particular level, which is known as the lifting condensation level. Lifting condensation level. After that, based on that energy, some energy which still it has, and it becomes saturated after this saturation level. So vapors get saturated. Okay, so the vapors get saturated here, and this saturated vapor starts further cooling and it goes up. Still, you see in this region the temperature is lower than that, but it is the momentum which is given from the surface or surface processes like convection, which I will talk about that. So that process is actually lifting it up to this. Now this is known as the LFC, the level of free convection. Okay, and now after just passing this level of free convection, now you see the temperature of the parcel follows the saturated adiabatic lapse rate. Actually it was following from here only, but still the temperature was lower than the environment's temperature. But here, as it crosses the LFC, temperature of the parcel is now greater than this. So by the instability, the buoyancy is there, so it can move up to a level of neutral buoyancy where it will stop. So when this parcel is going, actually not only one parcel going, there are several parcels will be going, and this is creating clouds over this region. Okay, so this is the process of creating clouds over this region. Fine. So this, now here you have to apply energy by convection processes and things. So this is this negative energy, because you have to apply energy. So this is called convection inhibition energy. Because here work is done against the gravity. So that's why it has negative value, or called sign or sine many people. But here these are positive energy. Okay, this is known as the CAPE, convective available potential energy. I am not going into the details of the derivation of this CAPE and sine. Just this energy, you have to remember that this is by its own, it is going after LFC crosses. So that's why it is called CAPE, but it has to be applied when it was below the LCL or LFC. So that's why these are the negative energies. So for negative energies, the convective inhibition energy is negative. Now for thunderstorm events, when you see those thunderstorm events, this CAPE is actually much greater than CD. Then only possibility of thunderstorm is created. Means this area is larger as compared to this area. So it will be like this, that this is the thing, and like this. So this is more of positive, this is more of negative. This kind of situation comes. This is gamma S, this is gamma E, and this is gamma D. Fine. Some network issue is there, so sorry for that. So this is the situation when thunderstorm events occur. Okay. Now I will tell you in short some processes uh, which will tell us about how this energy is provided so that it can lift the parcel to this LCL level. So first is using thermals. What happens is that in the daytime temperature rises, so this automatically has more temperature, so this parcel tends to rise because T increases here as compared to the environment. This parcel increases, parcel's temperature increases, so it rises up. This is rising air due to buoyancy is actually your thermals, or the parcels are known as the thermals. It goes automatically based on the buoyancy. We have discussed what are the buoyancy, so I will not take too much time in this. Another is the low pressure. Sorry. So suppose there is a low pressure form. Why do the low pressure form? This low pressure forms because of, suppose there is a high temperature. So this, all those column, if you see, all those molecules or whatever the gases which are present, they move randomly because it's a high pressure. Now as they move randomly and move up, so this region becomes vacant, as a result of which winds from all region comes here and converges. As it converges, it cannot go down because it is the surface, so it has to move up. So in this way, any parcel, if it is present over here, so this parcel will be carried up to LCL and then up to LFC, that is lifting condensation level, and then up to the level of free convection. So in the level of free convection, then it has its own energy to go forward. So this is another way through which the convective inhibition energy is provided. So this is the convective inhibition energy, also process is convection. Okay. The third thing is the fronts. Now fronts I have to discuss somewhat. For the fronts, you need to know about the air masses. What are those air masses? So air masses are, so first let me see, this is air masses. So it's a large chunk of or volume of air, large volume of air, whose vertical variation of different variables like temperature, pressure, relative humidity, these variables, there may be some vertical variation, but horizontally they remain same. Horizontally remain same. So these variables remain same horizontally. So this is nothing but an air mass. Sometimes you can notice that it is CP, continental polar, or sea warm. Okay, so it is hot and continental air, like that way. So I will show in the next class an air mass picture over the world. So this is called the air mass. Now air masses can be classified in terms of temperature as cold or warm air masses. And this cold and warm air masses actually brings the concept of fronts based on the speed of the cold air mass and warm air mass. So these fronts, there are two kinds of fronts. Oh sorry, there are four fronts. One is stationary, second is cold, third is warm, and fourth is occluded. Occluded means what? Hidden. So I will show each of them, and its sign, there is a symbol is also there. So first is stationary. So what is happening in the stationary? this is a cold air mass and this is a warm air mass, and they are not moving, just they are oppositely resisting each other, but none of the cold or the warm air masses have greater velocity than the other, so it is just kept like that. So this is the stationary front where the front is not moving, kind of this is the situation. So in the opposite direction, so for cold front is represented by these icicles, and warm front is represented by like this semicircles. Okay, so this way it is represented. This is stationary front. Second is the cold front. I have already uh, given the symbol of the cold front, but I will show much more. So suppose this is a cold air mass and there is a warm air mass, but the cold air mass is traveling faster, so warm air mass will go like this. Okay, and as the cold air mass above which the warm air mass is going, of course warm air mass cannot go below this because warm air mass is lighter. Okay, so as it goes above, what happens, this the contact point, this contact point will, this is warm and moist, of course warm air has more moisture, so this moisture generally cools and condenses and cloud starts forming over this, so big thunder clouds forms. Okay. Big thunder clouds form, and the direction of the cold front will be, see these icicles point in the direction of the cold air mass moving, so the cold front is moving in this. Why? Because the cold air mass's velocity is much greater than that of the warm air mass. Third thing is that, so you can see that the warm air mass and cold air mass, this lifting of the warm air mass is actually providing that convection inhibition energy in the earlier graph which I have already told. So again there is a warm air mass. What is happening in the warm air mass? So there is a cold air, and warm air mass is traveling faster as compared to the cold air mass. So here also some clouds are formed, not big straight what you call as cumulonimbus cloud or thunder clouds. I will show the different classification, but clouds forms, rain also occurs, but warm front's direction will be in this, in which direction it is moving, that is the important. And the fourth is the occluded front. Fourth is the occluded front. What is this occluded front? Suppose this is a cold air mass, this is another cold air mass, okay, and in between there is warm air mass which is present, so it is hidden, therefore it is, its symbol is like this. So in all in the same side. These generally are formed in the extratropical cyclones. No need to worry about this, but extratropical cyclones, these occluded form fronts as well as warm and cold fronts can be seen. So this frontal lifting, actually not fronts but frontal lifting process, which you can see in this cold and the warm front, the frontal lifting can provide the Cine, that negative energy through which the parcel can reach up to LCL. Okay, so this is another process. And now is the orographic lifting. What happens in this orographic lifting is that, see, this is a mountain, orography means mountains, okay, and winds which are coming in this direction, warm moist winds, warm or moist winds, they generally come and therefore they tend to attack in this direction but cannot penetrate this, so it has to go up. As it goes up, the LCL is automatically reached because LC is nothing but at a particular height. So it's a lifting condensation level, some height at which the temperature becomes equal to TD, the dew point, or the relative humidity becomes 100%. So their lifting condensation level is reached, and then by its own it can go, but still there is some force. So this is the process of orographic lifting. Fine. Another thing which I have missed here is this one. See, lifting condensation level is that level where T is equal to T dew, or relative humidity is equal to 100%. Fine. Okay. Now another thing, interesting thing which I want to show is that when this all moisture is shaded up to this region, the air becomes dry. Okay. And when it falls, see, this is the windward side. Why? Because wind is coming from this. And this is the leeward side. Okay. So when all the moistures are shed over here, parcel becomes dry. Now this dry parcel will fall, and its increment as it falls down, temperature increases, of course, because as we go up, pressure decreases, volume increases, and temperature decreases. But here, as it goes down, its pressure increases, volume decreases, temperature increases. So temperature should increase, right? So as the temperature increase, this will increase at 9.8 degrees Celsius per kilometer. That is DALR, dry adiabatic lapse rate. So you can see 10 becomes 20, it becomes 30, and becomes 40. So remember always, in the leeward side, when all the moisture is shed by the parcel, it becomes dry, and using that same dry adiabatic rate, not lapse rate because it is not the decrement, now it will be increment. Why? Because the pressure increases as parcel goes down. So temperature increases. Okay. So this is another thing which I want to show. Okay. Next is the warm and the cold cloud processes. One is your coalition coalescence process for the warm clouds, and for the cold clouds, Bergeron's theory is there, and different types of clouds, which is the last slide which I have. Okay, so let us quickly discuss this warm and cold cloud processes. Okay. So warm cloud processes. So what is a warm cloud? Warm clouds are those clouds whose top temperature is greater than minus 15 degrees Celsius. These are warm clouds. But if it is less than minus 15 degrees Celsius up to say minus 40 degrees Celsius, so cold clouds whose top temperature is nearly greater than, or I would say less than, minus 20 degrees Celsius. Okay, minus 20 degrees Celsius. So for warm clouds, generally in the tropics, we have coalition coalescence process. So this is the coalition coalescence process. So here what happens is that, so suppose a cloud droplet which is formed, it goes up due to some updraft, but as it goes to a height where updraft is exactly equal to the terminal velocity, that is, it balances just the gravity, the updraft velocity actually balances the gravity, it falls. As it falls, it interacts with different small droplets and results into a big droplets by the collision process. Okay, so this coalescence is nothing but merging of droplets by collision. Simple process, fairly simple process, occurs in your tropics. Cloud droplets generally of the order of 100 micrometer, and raindrop size is about say 2000 to 5000 micrometer. Fine. And these big droplets occurs as rain. For the cold clouds, we have three levels. One is the very top level, middle level, and the lower level of the clouds. Okay, so in the lower levels, only water droplets are present. Hello. So again a problem in the internet connectivity. Just a minute. Yeah. So this is the top layer, this is the middle layer, and this is the lower layer. So this is the cold clouds, okay? Cold clouds, mid latitudes or high latitudes. Okay, and this process is known as the Bergeron's process. So what happens here is that this is in the lower layer, only water droplets dominates. So it is only water droplets. So suppose this is a 0 degree Celsius isotherm. So water droplet still remains. Okay, so these water droplets are known as the supercooled liquids. Okay, these are the supercooled liquids. That is why we call this, because below 0 degree Celsius it ideally should be ice crystals, but it is still in the form of water. It is still in the form of water. Ideally it should be ice crystals below 0 degree Celsius, but as we go high up in the middle layer, ice crystals starts forming, and still water droplets are still there. Again, these are supercooled liquids, but in the top, ice crystals only dominate. So what happens is that in this process, one water droplet, if it evaporates, it falls on this ice crystal and so it increases its mass, and these ice crystals forms larger, and as a result of which it falls out as rain. So what is happening? Due to entrainment or due to evaporation, water molecules gets evaporated from here and it falls on the, or it condenses on the ice crystals. Ice crystals becomes heavy due to this and it falls out as rain. So it's a simple process. Fine. And the last is the different types of clouds. So one is the high clouds, middle level clouds and low clouds. So low clouds are like stratus, stratocumulus. Okay. I would not say that cumulus and cumulonimbus are low clouds. These are nothing but the developing clouds. Developing clouds. See, it develops from the low level to high level. And this thing, if you see, this suddenly going like this is known as the anvil shape. Okay, and this is the cumulus, it is also the developing clouds. But stratus and stratocumulus, these are low level clouds. Nimbostratus is also a low level clouds. See, nimbus means precipitation bearing. Precipitation bearing clouds are nimbostratus clouds. And middle level clouds are represented by alto cumulus and alto stratus. You try to look at the shapes, how it happens, and particularly these cumulonimbus clouds, these are nothing but the thunder clouds. When the thunderstorm occurs, these kind of clouds forms. And because why these clouds are forming? Because its cape, convective available potential energy, is very high. So parcel can go on its own to a larger height. So that's why this is thunder clouds. Okay, and the high level clouds are cirrostratus, cirrus, and cirrocumulus, and these are generally found during winters. You can find out in the northern India. These kind of clouds are formed. Okay, so these are the very basic different types of clouds which are there. So you have to remember which are high clouds, which are middle clouds, and which are low clouds. That's all. Fine. So that is the end, I think. Yeah. So I stop the presentation. Just see what is happening. Okay. So this PDF you will get, and recording link also you will get. And sorry for the interruptions today. There is a big network issue today. I stop sharing. Thank you very much. Goodbye.